Somewhere in a conversation window, on an ordinary night, someone typed 11 words into an artificial intelligence and asked it to answer the oldest question our species has ever asked. Who built the universe? And if it's this big, why haven't we heard from anyone else in it? What came back wasn't a comforting bedtime story. It was a cold, methodical argument, built piece by piece, that ends somewhere much darker than where it starts. Stay with me, because by the end of this, the silence of the night sky is going to feel very different to you. To understand why that question is so heavy, you have to actually feel the scale of what's being asked. The universe is about 13.8 billion years old. Within it, current estimates put the number of galaxies somewhere in the hundreds of billions, each one a slow-turning city containing hundreds of billions of stars of its own. Multiply that out across every galaxy, every star, every likely planet, and astronomers arrive at a number that's almost embarrassing to say out loud, somewhere in the neighborhood of a septillion planets. That's a 1 followed by 24 zeros. A trillion worlds, spinning in the dark, most never seen, never named, never touched by any eye at all. And on at least one of those worlds, something happened that, as far as we know, has happened nowhere else. Chemistry organized itself into biology. Biology organized itself into a nervous system. A nervous system organized itself into a species that stood upright, looked at the sky, and started asking questions about it. That's us. And the question we eventually landed on is the one that keeps astronomers up at night. If life happened here, on one very ordinary planet, orbiting one very ordinary star, in one very ordinary galaxy, and if there are that many other worlds out there, and if the universe is at almost 14 billion years to work with, why is the sky silent? Every reasonable calculation says it shouldn't be. A universe this old, this large, and this rich in raw material for life should be loud. It should be humming with signals, littered with the evidence of other minds, other civilizations rising and falling across deep time. Instead, when we point our instruments at the dark and listen, we get nothing. No signals. No engineering on a scale we could detect. No one has ever called, and as far as we can tell, no one has ever answered. That gap between what the math predicts and what we actually observe has a name, the Fermi paradox. It started, appropriately enough, over lunch. The year was 1950, at Los Alamos, the same New Mexico desert lab where the atomic bomb had been developed just a few years earlier. A handful of physicists were walking to the cafeteria, chatting about flying saucers and the odds of alien life, the way people do. The conversation moved on to other topics. But one of the men at the table, the physicist Enrico Fermi, kept turning it over quietly in his head. Partway through the meal, seemingly out of nowhere, he asked the table a simple question. Where is everybody? It sounds almost like a throwaway line, but Fermi was doing what Fermi always did, which was running rough arithmetic in his head. And the arithmetic was troubling. Given the age of the galaxy, given the sheer number of stars in it, and given even modest assumptions about how often life, intelligence, and technology might arise, the Milky Way should have been colonized many times over by now. A civilization only slightly more advanced than ours, expanding outward at even a small fraction of the speed of light using self-replicating probes, could sweep across the entire galaxy in a few million years. Against a galaxy that's existed for over 10 billion years, a few million years is nothing. It's a rounding error, so the galaxy should be full. Instead, it looks empty. To be precise, this isn't a paradox in the strict logical sense, where two things directly contradict each other. It's something subtler, and honestly more unsettling. It's an unresolved gap between theory and observation. Our best understanding of probability, chemistry, and the sheer abundance of worlds says a universe should be teeming with intelligent life. Our best observations, gathered over decades of careful searching, say we see nothing. Theory says full. Evidence says empty. For over 70 years, some of the best minds in science have tried to close that gap, and nobody has managed it yet. Now, imagine handing that question to a system that has no personal stake, in which answer turns out to be true. No hope that the sky is full of friends, no fear of what it might mean if we're alone, no religious or emotional commitment to any particular outcome. That's roughly what happens when you put this question to a large language model like Grok, built by Elon Musk's company Grok AI. It's worth being precise about what that actually means. A model like this isn't an oracle with secret access to the cosmos. It doesn't know anything Fermi's intellectual descendants haven't already published. What it's good at is holding every proposed explanation in view at once, weighing them against each other without ego, and laying out, in plain language, which arguments actually hold weight and which ones only sound good. When you push a system like that to work through, why haven't we heard from anyone? What comes back isn't a reassuring paragraph telling you not to worry, that they are just far away and we'll find them eventually. It reads more like a case file assembled by a very calm, very unsentimental analyst. It takes the leading hypotheses that real astronomers, physicists, and philosophers have argued about for decades, lines them up side by side, and doesn't play favorites. It says, in effect, here's what each explanation claims, here's how much weight it can actually bear, and here's exactly where it falls apart. And working through that list honestly, the explanation family it keeps circling back to is not the comforting one. To understand why that matters, you have to understand how much has changed since Fermi first scribbled his napkin math in 1950. Back then, he was making a massive, unproven assumption that planets were common, that stars like our sun had worlds orbiting them at all. And here's the part most people don't realize. For nearly the entire span of human history, right up until the final years of the 20th century, we had zero direct evidence that any of this was true. We could see stars. We could not see a single planet orbiting any of them. For all anyone knew, our solar system might have been a cosmic fluke, the only place where planets happened to gather around a star. That changed fast. In the mid-1990s, astronomers detected the first confirmed planets orbiting other sun-like stars, picking up faint wobbles and star-like caused by unseen companions tugging on them. Then, in 2009, NASA launched a space telescope that rewrote the picture entirely. It stared at a single patch of sky containing more than 150,000 stars for years at a stretch, waiting for the tiny, brief dimming caused by a planet passing in front of its star. What it found broke the question wide open. Planets weren't rare. They were the rule. Our galaxy alone likely contains tens of billions of planets sitting in the temperate zone where liquid water could exist, where surface is neither scorched nor frozen, where life, as far as we understand it, has a fighting chance. Fermi's assumption turned out to be an understatement. The galaxy is drowning in worlds. And that only sharpens the question. Because if worlds are everywhere and the raw ingredient of life are everywhere, the silence stops looking like a simple gap in our knowledge. It starts looking like the strangest fact we've ever observed about the universe. That's where the reasoning naturally turns toward the ingredient of life itself, and toward an even older question than Fermi's. How hard is it, really, to get from dead matter to something that thinks and looks up at the sky? Hey, it's worth laying out the case for optimism first, the way a careful scientist would, before testing it. The building blocks of life aren't exotic or rare. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur form the backbone of every living thing on Earth, and none of them are cosmic rarities. They are forged inside dying stars and scattered across space in enormous drifting clouds. Carbon is the fourth most abundant element in the known universe. Oxygen isn't far behind. The universe isn't stingy with the raw material of biology. It manufactures it constantly, in every galaxy, in quantities that are hard to even conceptualize. It goes further than raw elements. 2. When astronomers examine cold clouds of gas drifting between stars, they find complex organic molecules already assembling themselves with no help from anything alive. When scientists study ancient meteorites, rocks older than Earth itself, they find amino acids, the basic building blocks of proteins, formed in the vacuum of space long before our planet existed. On Titan, a frozen moon orbiting Saturn wrapped in a thick orange haze, spacecraft instruments have detected a rich stew of organic chemistry, the exact kind of carbon-based molecules that, on a warmer world, might be the first tentative steps towards something alive. The chemistry of life doesn't look like a miracle that happened once, in one place, by extraordinary luck. It looks like a process the universe runs constantly, whenever you give it time and the right conditions. Then there's a detail that has genuinely unsettled biologists for years, and it's one of the strongest pieces of evidence in the whole argument. Earth formed roughly 4.5 billion years ago as a molten, cratered wreck, bombarded constantly by asteroids, its surface a rolling ocean of magma. It took hundreds of millions of years just for the planet to cool enough for liquid water to gather on its surface. And yet, almost the moment conditions became survivable, life shows up in the geological record. The chemical fingerprints of living organisms appear in some of the oldest rocks we can find, laid down when Earth was still young, unstable, and violent. Life didn't wait around for some improbable billion-year fluke to align. It arrived early, almost as if it had been waiting for the door to open. That points toward a specific and somewhat unsettling conclusion. If life tends to arise quickly whenever the conditions allow it, then maybe the origin of life itself isn't the hard step in this whole process. Maybe turning dead chemistry into a living cell is something the universe does readily, any time a warm, wet, mineral-rich world settles into orbit around a reasonably stable star. Combine that with tens of billions of potentially habitable planets in our galaxy alone, multiply it across hundreds of billions of other galaxies, and the math becomes almost impossible to hold in your head. The number of worlds where life could plausibly have gotten started isn't just large. It's a number with no real emotional meaning to a human brain, because our brains were never built to process quantities like that. And if even a tiny fraction of those worlds went on to produce not just life, but intelligence, the sky should be loud with evidence of it. It should be almost impossible to look up on a clear night and not see some fingerprint left behind by a civilization older than our own. Which brings us to the piece that turns this from a puzzle into something closer to a warning: time. We tend to assume, almost without noticing we're assuming it, that if other civilizations exist, they exist roughly now, at roughly our level of development, discovering radio waves around the same general point in cosmic history that we did. There's no reason to believe that. The Milky Way is somewhere around 13 billion years old. Our Sun and our Earth are late arrivals by comparison, only about 4.5 billion years old, forming long after the galaxy had already been manufacturing stars and planets for billions of years. There were worlds cooling, gathering oceans, and possibly stirring with early life while our own sun was still just a cloud of gas. Some stars out there are older than ours by 5, 6, 7 billion years. Sit with what that actually means. It took modern humans roughly 200,000 years to go from the first anatomically modern people to building radio telescopes, and only about a century to go from the first powered flight to spacecraft leaving the solar system. A single human lifetime spans the distance between horse-drawn transportation and probes crossing into interstellar space. Now imagine a civilization that didn't get a 100-year head start on us, but a 1,000,000-year head start. Not 100 million, just 1 million, which on a galactic timescale is barely a blink. What would a species capable of 1,000,000 continuous years of technological progress be able to do? Nobody can answer that with any confidence, and it's worth being honest about that uncertainty rather than pretending otherwise. But we can say this much: a civilization that far ahead of us would likely possess capabilities that would look to us like magic or like the fundamental laws of physics themselves. They would have had time to spread, to build, to harness the energy output of entire stars, and to send self-replicating machines drifting from star system to star system, each one landing, constructing copies of itself, and launching those copies onward. This is the exact mathematics Fermi worked out over lunch in 1950, and it still holds up under modern scrutiny, even at speeds far slower than light. Even accounting for the enormous distances between stars, a single expanding civilization using self-replicating probe could plausibly sweep across the entire Milky Way in just a few million years. Set that a few million years against a galaxy that has existed for over 10 billion years, and the conclusion is uncomfortable. There's been time for this to happen, not once, but potentially thousands of times over. By the numbers, the galaxy should already be settled. Every direction we point our instrument should reveal some trace of a civilization that got here long before we ever opened our eyes. Instead, there's nothing.